So I am one of the, I guess, 2 local speakers. So I just took a subway over. I used to work across the street, but now, unfortunately, we're up by Times Square. So it's a much better area to be. But I'm happy to come down for today. As Taylor said, I work at MongoDB. I'm going to spend the next 40 minutes talking about how you can deploy this on AWS. And maybe we'll have time for some async PHP. Just kidding. So Igor is in the audience up front, and I'm hoping he doesn't ask me questions later, but I'm going to be talking about React PHP and just doing asynchronous programming in PHP. And this is basically a project Igor Wheeler, you're going to hear from him tomorrow, blow our minds at some math talk. But this is essentially a framework that he created with Chris Bowden. And so I'm going to start off before we talk about PHP, just look about how we might make a web server. This is essentially the hello world of asynchronous programming. And so if you're familiar with Node.js, it's bootstrapping a web server is pretty straightforward. They have the necessary classes in there. So we can kind of just construct a server object, and then it's all event-driven. So we'd say on it, when a web request comes in, we'll just write out a response code. We'll write out the header. We'll write out the actual body of the response. And then we could take the server object and say, let's go listen on a port. And so you run Node.js, and basically your application should end up listening on you could listen on multiple ports and things like that. And then Python, doing asynchronous programming in Python is a little bit trickier. So there's a bunch of convoluted frameworks to do it. Twisted is one of them. And depending who you talk to, you might have Python developers that absolutely hate working with Twisted. Other ones think it's OK. And in Twisted, it's a little bit more verbose. But the same concept is the same. We basically have this page resource. And when the event comes in this case, Twisted already kind of does the routing for us. So we can just listen on it on the same kind of port and then fire back a request. And so these are both really good examples of we could service multiple requests at once. But it's a PHP conference, so let's look at how we might do this in PHP. And so if you've, how many people are familiar with the stream, all like the stream functions in PHP? Or has ever gone to that part of the documentation? So there's a bunch of nifty functions there, and some of the ones that React builds upon for this, we have stream socket server, which lets us set up the same kind of thing where we could listen on a particular port and a IP address, and just as incoming stuff comes in, we could read off the socket. But there's a distinct difference here. So we're still writing to the socket and closing it when we're done. But the main problem has to do with when we accept the sockets. And so you notice we do a -1. And that's because PHP really doesn't have any way to do any asynchronous programming of its own. It's not an asynchronous, unlike Node.js, like the PHP runtime is not inherently asynchronous. And so when we're dealing with sockets and reading stuff in PHP, we typically do blocking I/O, which means I'm going to listen on this particular port or this particular socket and just wait until some input comes in. And the problem is when we're blocking, we really can't do we can't do other CPU activities. We can't run any other functions or listen on other ports. And so explain why this is actually a problem if it's not already obvious. So when we're dealing with any heavy I/O application, we're going to basically be taking input, writing output, and then periodically act on that. And so that's going to be our CPU time. And so if we're thinking in PHP's model where we're going to wait for that I/O to come in and then do some processing or run a function with it, maybe create our PHP request, and then after that we want to listen to more I/O, they're going to be occurring sequentially. So what we'd like to do is, ideally, if we could parallelize this. So this is a very synchronous approach. There's no parallelization. It's not scalable because as requests come in, they could just build up, and we can only handle one at a time. And I'll also note the blocks here really aren't drawn to scale. The I/O is infinitesimally, that's the wrong word, but it's much, much larger than the CPU time. And so maybe you've seen other presentations or this table looks familiar. Sometimes the scale is a bit different. They might say they might phrase it in terms of accessing the CPU is 1 day, and then when we have to go to disk, that's years or millenniums and things like that. But the things that we actually care about are looking at the actual network and the disk storage throughput. So when we're dealing with the CPU, we're reading memory, we're reading registers in the CPU. It's maybe on the scale of a nanosecond or less, and that number kind of keeps creeping down. But the numbers that are way much higher are when we're dealing with accessing network or disk storage. Whether that's locally or, God forbid, we have to go across data centers or across much larger distances. And so the network and the disk I/O is really where everything slows down. The CPU, we have a lot of capability there. And so this isn't anything new. And in 2001, Dan Kegel came up with a wrote, it wasn't really a blog post. I don't know, people didn't really have blogs back then. But he wrote an article on his website where he addressed the C10K problem. And this was back from the days where, if anyone remembers, like cdrom.com or 2cows FTP sites. So back in the days where they had these old FTP servers. And he said, around 2001, I could have a machine, a gigahertz machine with 2 gigs of RAM and a gigabit network bandwidth, which was pretty impressive at the time. And I should be able to serve concurrently 20,000 different clients. And they really all just need to, if I'm just sending a packet of bytes or 50 kilobytes back to them, they really just need a fraction of the CPU, a fraction of the network speed, and the disk storage. So it's really not a I/O problem. The hardware isn't the bottleneck. It's a matter of how we're structuring our CPU. Like, we should have the capabilities to service this number of requests. And if you've seen any benchmarks on like how benchmarks on like Node.js, how many requests it might handle at a time on very modest hardware, just by interleaving the I/O and stuff, there is a lot of room to improve upon the serial handle I/O, do CPU, handle I/O. And so the different approaches that we can go to solving this, and the first one that might jump to your mind as a computer science developer or a student of computer science might be threading. And so in threading's case, we're asking the CPU to run multiple functions at once or multiple threads of execution at once. So this is definitely more parallelism. And we can see the I/O, the operating system is going to take care of the I/O for us, so it's going to do that all concurrently. And then if we had our individual functions or thread classes running, if you're working in something like Java or C++, we could have all of them run concurrently at the same time. The trade-off here is that every time the CPU has to negotiate with threads, there's context switching. We have to shuffle memory around. And additionally, it makes writing our application quite a bit more difficult, because sometimes we have to sync up threads. Multiple threads might depend on each other. And so the alternative here is maybe in PHP, some people deal with process pools. So they'll fork a bunch of processes and then have them run concurrently. And that's kind of essentially what happens when we do threading, except that's happening within the language. But just ways to achieve parallelism and just have multiple units of instruction run at the same time. But this does give us better ways to access all the I/O concurrently. The alternative is to do non-blocking I/O, which is going to be the approach that we're going to talk about today. And this is all going to be event-driven. So we have the I/O blocks, and they basically take as long as they take. And maybe they happen to finish around the same time or not. But basically, when an I/O block is ready, we have a callback for it, ready to handle it. And we can immediately invoke that. And then knowing that since we're in a single-threaded environment here, we can only run one function or one thread of execution at a time. But as soon as that first CPU block is done handling the first I/O, we realized at that point the second I/O block happened to finish while that was going on. And so we know, OK, well, on the third line, that's the next CPU block we have to go and trigger, because that I/O is ready and waiting. And by the time that's done, there is another I/O block came in, and we're available to read and write to that stream, so the last execution can come in. Comparing this to threads, you could do more at the same time with threading. This is a more straightforward approach with, if you're comfortable dealing with the callbacks, where we could still work within, we don't have to go into threading and we can still stick with a single-threaded approach. And so this is really the same thing that, if we, I guess, contrast the difference between some of the Apache server models and what Nginx does. So Nginx is very event-driven. It basically applies this mechanism, as does Node.js. And when we're looking at I/O and waiting for it, the I/O could be network traffic. It might be blocks of memory. So there's different low-level C functions where we can basically ask the operating system, am I ready to read from this bit of memory yet, this file that's been mapped, or am I ready to read off this network socket? So that's basically how we know that I/O blocks are ready. We could just poll the operating system. And so ways that we could achieve concurrency in PHP. If you peruse all documentation, there's a lot of different APIs available. So one of them is an extension, which I believe it's one of the ones that doesn't run on Windows. I could be wrong about that, but pthreads, which is P stands for POSIX. So this is like the Unix and Linux convention for threading. So that was just a C library that it was ported over to PHP. There's ways to deal with, I mentioned forking multiple processes, having like a process pool, and just running background processes that go off and run at the same time. So we have multiple ways to do that. We can fork a PHP process. We can exec another program. Maybe it's a PHP, maybe it's a shell script or a Python program, anything. And then we have the functions for dealing with polling I/O. So with sockets, we can basically ask the operating system, am I ready to read from this? Or if we're dealing with streams, which is a nice kind of abstraction on top of raw sockets. And additionally, things like the curl library, they have ways to do async programming as well. Or rather, just work on multiple I/O streams at once. But the one I want to focus on today is what React uses is the select. So if you're familiar with man pages, basically the effing manual for Linux and Unix. So with man pages, the select goes back. It's a really old system call. And we just give it the file descriptors. So in PHP's case, when you open a file or you get a file resource, it's comparable to what we're passing in here. We give it a list of file descriptors, and we say, I'd like to wait for this long for my polling time. So maybe I want to wait indefinitely. Maybe I just want to wait a second or half a second. And I'd like you to return to me, tell me which ones are ready to read to write to read from, and which ones may be closed, if there's some exception that happened on them. And so this is what is implemented in PHP. And notice that it's multiplexing. Essentially, that just means we're dealing with multiple I/O streams in one operation. So we can pull multiple streams at once. And so an example in PHP, and this is really kind of the internal code of what begin to understand what React does inside. So we have our read streams, some write streams, and some exceptions. So whatever those may be. We'll pass it in the stream select. And so this is basically an array of streams, an array of writable streams, and then except is just passed by reference. So we want to capture the output there. And one is going to tell us that we'll wait for 1 second. And then when this does return, it'll block for 1 second, and then control comes back to us. And now the readable ones, the readable and writables will just be whatever originally we sent in all the ones we want to monitor. When this returns, now the array just contains the ones that are actually ready to be read or ready to be written to. So this is kind of the loop that a async PHP application would go through, or just a PHP that's dealing with juggling multiple streams and trying to read and write to them. And so some other things we could do here, we can use a null timeout, and that's basically block indefinitely or block until one of them is readable or writable, some activity occurs. And so you might want to block indefinitely if you really have nothing else to run. So if you're just a web server, and unless you're actually servicing requests, there's nothing for you to do. So you could block indefinitely. What you wouldn't want to do is you can not block at all and just kind of poll instantaneously. And you wouldn't want to do that in a tight loop, because then you're just constantly running a CPU instruction. So it's like doing a while true and just watching your CPU spike. So it is important that you have some actual blocking, and that allows the operating system to let other, whether your database server or any other things on your processor run without monopolizing things. And so React comes back to having the concept of an event loop. And so the event loop kind of encapsulate that the iteration where we're just going to be polling for whatever I/O happens to be, whether it's disk or network sockets or maybe other processes and their standard in and output. And additionally to the streams, we'll also have timers, because there's actual code that we have to run. Maybe not everything is just responding or reading or writing from a stream. So there might be different callbacks that we want to register. And then each loop operation it would consider it as a tick. So similar, we could have things that run once every loop iteration. And the ticks are going to be in between. Every time we do the polling, we're going to wait until some I/O is ready. And then we'll queue up events to respond to the I/O, and then execute a tick in case there's extra processing to do. And so in this case, it's OK that we're blocking until there's some I/O to be done. So we would use a null timeout there. And then the tick, when a tick comes in, if there's anything that's queued up, maybe we said something should run in the next 5 seconds, that's all the points where that will be executed. And then the polling timeout, we could also be calculated. If we know that we want to run something 5 seconds from now, instead of polling indefinitely, we could just poll for 5 seconds. And then if I/O happens to come in the 5 seconds, that's great. Otherwise, we know that we need to have a tick, because the next scheduled operation is to happen in 5 seconds. So that's basically how the event loop would organize. How there's I/O that's happening, but we also have things that maybe have to happen at regular intervals that we'd still like to run. And then if there's nothing to do, then basically the loop ends. So similar, basically your PHP application, in this case, the application just invokes the event loop, and it just continues until there's nothing left to do. So kind of like if you were to start up Nginx, it starts up, listens to requests and everything. In that case, you probably run it indefinitely, but in the PHP case, you're probably running an application for for some actual purpose. So if there's nothing scheduled and there's no open sockets or anything like that, there's nothing to listen on, then we can just close the application. And so this brings us to React. So it's event-driven model, so we're going to be using a lot of callbacks. Probably no super closures. That's too intense. It's non-blocking I/O, so we're going to be using select for that. And it's obviously written with PHP because we can't be bothered to learn other languages. And so that's really, Igor likes to implement everything in PHP from other languages. So a hello world example. So this is going to be slightly the same concept what we did earlier of creating a web server, but hello world in React's case. So we have that event loop. We can create that. It's a static method. I don't think it's actually a facade, though. And then we're going to create a socket, create the HTTP server, and then register. So this basically looks very similar to the Node.js example. We say, for the HTTP server, there's going to be some event called request. So when requests come in, my callback is going to be run, and I'll have this request and response object. And from there, I can investigate the request if I like. Maybe I need to do some routing. But in this hello world example, I'm just going to dump out something. I'll say the socket's supposed to listen on a certain port. But until I call loop run, there's nothing's actually bound. We're not actually blocking or listening in any network traffic. So usually you'll set up your application, set up all your callbacks, and then loop run is kind of like the front-end controller of your framework where you have where your requests come in and you kind of trigger maybe it's like the Symfony HTTP kernel, and that gets things started. And so the name of React basically comes from, it wasn't cooked up for no reason. It actually based on a design pattern called the Reactor Pattern. And so this involves a couple of components, which I'll just talk at a high level. So we have this demultiplexer. It's a job of that basically to deal with, so I mentioned multiplexing is dealing with multiple I/O streams. So the demultiplexer has to negotiate listening on all these streams and ensuring that we can dispatch different events as they come in. Additionally, we have the different resources. So those might be streams. It could be other processes, other file handlers. Dispatcher is going to be our event dispatcher. And so we're going to see React has a separate component for that. And then request handlers at a higher level are, as the events come in, those are basically our callback methods that get dispatched. There's an alternative designs to, so a lot of frameworks like Node.js is a reactive pattern. There's also, for the ambitious C++ developers, they have a proactive pattern, which is like asynchronous all the way down. So with React, when we dispatch our request handlers, we're running them synchronously. So those do block. So there's more convoluted patterns that exist out there if you wanted to go full async, but not in PHP. And so to just cover some of the high-level components of what the stack looks like. So there's the event loop, which is basically coordinating everything. And this is a library called Eveniment, or Evenime, if I'm pronouncing that right. Evenmo? OK, sorry. My Europe language skills are rough. And so the event dispatcher here is based on Node.js, their API for event emitting. And then built on, the event loop underneath uses the event emitter. And on top of that, one of the first things we're going to deal with are streams. So whether these are network connections or disk or standard in, standard out. On top of that, we have the concept of a socket. And those are the actual established TCP connections. And then beyond there, we start adding these services. So React happens, some of the first ones that were created, we have HTTP, which is inherently the server. We have HTTP client and DNS. You may be wondering why DNS is there. So just resolving domain names, if we rely on PHP, the DNS resolution is synchronous, so that would block. So one of the first components Igor had to make was a DNS resolver that worked off of the I/O stream so that we can basically say, I'd like to resolve this domain name and get back to me when you've actually talked to the name server and resolved it. And that makes the HTTP client not be as stupid and blocking whenever it has to resolve anything. And on top of this, there's a bunch of other interesting things that have been added. So there's an IRC server. Chris Bowden, the other lead developer on React, has a WebSockets library called Ratchet. There's also drivers for things like Redis and ZeroMQ. And then something to control little aerial drones, because those are popular these days. One of the contributions I made last year, which was the whole reason that I submitted the abstract for this and came up with the idea for the talk, I added a component to do child process. And I have an example that uses this later on. But this is basically I want to be able to fork a process to the background and add its standard in and standard out and standard error as streams that I can interact with asynchronously. And so that was, instead of doing just like network communication, I'd actually just want to fork some background process. And so that's helpful in cases where, so we have things like Redis and ZeroMQ. You'll notice there's not a lot of, like there is no asynchronous way to interact with MySQL. So one of the neat things with child processes, we can kind of fork a process and use these blocking database drivers to do your work, and then React can still talk to it over the streams asynchronously. But to dive into the event loop, so the goal here is we want to be able to track these readable, writable streams and then monitor them as things come in. We're going to want to dispatch our handlers on them. There might be different, I mentioned there's timers, so maybe there's things that you want to do one time after a set time, or there's interval timers. So there's, maybe it's like collecting logging information or just tracking stats or memory, or just regularly executing, think of like a kind of like your own cron within your event loop. And then there's actually multiple implementations of the event loop. So there obviously has to be one that is pure PHP, and so that's called the stream select loop. And so we already looked at what the stream select is. That's essentially the PHP's little wrapper around C's select function. But additionally, if you've browsed PECL and some of the PHP extensions, you'll notice that there's actual asynchronous and like libevent has been ported over to PHP. So there are two other implementations, or we think of them as event loop drivers, that can be used instead of the pure software mode. The first one uses libevent, and that's the libevent loop. And then there's also libev loop, which uses libev. Libev is what originally I think Node.js was using, and they've since moved over to libuv, which is a less stable PHP extension. So React does not have a stable driver for that yet, but I think there is a pull request for it. So I would hesitate to say using this in a production environment, but yes, many people are using React in a production environment. They probably do not want to use stream select loop. They'd want the better performance of using libevent or libev, just for the actual, it's less processing overhead in PHP to run. So we could actually register our PHP callbacks directly with those two C libraries. And so an example of what the event loop looks like, in this case, it's another HTTP server. But I'm not going to be using React's raw streams yet. I just want to highlight what the actual the raw server does. So in this case, we're using some raw streams here. So I'm going to use PHP to create a socket server. And this basically gives me a stream resource that I can read and write to as connections come in. And with the loop, I want to register this resource with it. So just monitor it when there's I/O activity there. And as it comes in, I'll basically, if there's something to read, that means I have a connection. So I can use PHP's PHP stream methods here to access the connection, create some data as a response, and then add a writable stream, which I'm going to ask React to asynchronously write this back. I don't want to, if I didn't add a write stream and I just tried to maybe f-write to the file or just write to it, it might block if there wasn't able to write. Probably not for 50 bytes that I have here, but in a larger response payload, if you're sending back like a file download, you could very well block if you tried to write it all at once. And so what will happen inside this callback, my callback gets invoked every time the writable stream is accepting data. And I'll basically try to write as much as I can at a given time. And if at any point, if fwrite returns, which means like I've kind of filled up PHP's buffer to write to that socket, I'll just truncate this and just remember that I have less data. I still have data left over to write down the line. And so in this example, I can still handle multiple incoming requests. So each one will get its own callback registered and a writable stream after I accept the connection. But working with the actual raw PHP streams is not nearly as, it's not as convenient as using these raw stream underscore functions. So React introduces these stream classes to wrap the native PHP streams. And so these are basically just OO wrapped around the original resources. And we can register the streams themselves with the event loop, so we don't have to go to the stream knows about the event loop. We can, it connects very nicely with like the socket servers and things like that. The main two kinds of streams, and we'll see there's extra classes around these, but they come down to being a stream could either be readable or writable. We might have streams that compose both behaviors. But we could also connect streams to one another in sequence and kind of turn them into Legos where we can just build more complex flows of data by putting streams together. And there's also streams that deal with buffering of data, so we don't have to, interacting with the streams, they can internally have their own buffers so that we can write to them, and they can not basically make the data storage a lot less blocking, and friendlier to work with by having the buffers. So just going to look at some of the interfaces. So a readable stream, whether or not it's readable, basically if it's available to read from. We can pause and resume streams. We can close them. And piping would just be connecting this readable stream over to a writable stream so that the data can just flow directly. We don't have to set up manual. Just internally, this is going to set up kind of the two events necessary on each stream so they can send data to each other. And if we have a stream, the different events that we might have, the one that you'll use most often is data, which means on data on this stream, that means there's data to read. So I could run my callback and take some action on that data, handle a HTTP request, whatever it might be. The flip side of this is the writable stream. So that's basically we write, or if we're going to end it and send the last bit of data. But the multiple events here, when we write, we basically send in as much data, and it'll write as much as possible. Drain will be the event that says, well, I previously was not available to write. I was kind of filled up, but now I'm empty. I'm available to write again. So drain is kind of the counterpart of the readable stream saying, oh, there's data available to be read. Drain means there's data available. There's room to actually write out. And so I worked really hard on these animated GIFs. So an example of streams, readable streams, if Mario is the data that we're passing along, goes right into a writable stream if we were to could pipe them together. Composite stream would just, we construct a stream and we give it two different streams in the constructor. And it basically creates one stream that we can both read from and write to. And then there's through streams, we can do things like filtering. So as you could have, if you wanted to, like people do this with their routers, where all the web data that comes in, they flip all the images upside down just to screw the people that are stealing their Wi-Fi password. So you can conceivably do something else. You could replace all instances of MongoDB with web scale in any of the data passing through your React streams. And then there's the other concept is a buffered sync. And what this is usable is for taking a writable stream and giving us an immediate return value, which is a promise. So quick segue. Talk about a little bit about promises. So how many people are familiar with this term, or maybe if you used, it comes up in jQuery, they have their implementation, certainly in a lot of Node.js frameworks. So originally there were no promises, and working with asynchronous programming was callback hell, where you your code would look like this, and then you'd go back out like that as you closed all your closing parentheses. So promises allow us to have better code structure, more testability, because we actually get these return values. We can assert that we get a response. We can mock out the different calls to things. There's a direct correspondence between the synchronous and async functions, so that we can kind of invoke some async function, and now all of a sudden, since it's returning something, it really feels like we're dealing with a synchronous function. And so the promise is really just a placeholder for saying, yes, I will have something for you to work with later. I'm just giving you this placeholder object right now. And so React's promises, I think, were added in, not in the original version, but in, was it 4 or 3? Or one of the later 3 versions. But within the last year, promises made it into React, the main repository. And they're based on CommonJS has a spec of promises. So it's the promises/a specification. If you search for promises, there's probably 1 million different implementations. And so the goal is, it'd be nice if our async functions return something that I could work with, so I don't have to have nesting all these different callbacks. And so deferred is the object that encapsulate a promise. So deferred represents that value that will be returned later. And a deferred, the different, I guess, values or objects that you might have here. A promise can ultimately be approved, where it's fulfilled, or it's rejected. And in between them, there might be some progress on whether, like if the data is coming in, we have a callback to where we can be notified of different updates. So all of these promises are basically what consumes the result of a deferred object. So this is just really a placeholder for some unit of work, some computation that will be returned, but it's not complete yet. And so an example of what this looks like in code, we'll just go right to that. It's, each time we have a promise, we can chain them together so that as a promise returns, if it happens to be fulfilled, I can give it a callback for the fulfillment that runs on that case, or if it's rejected, some other callback that will run in that case. And lastly, the progress callback. So these directly correspond to the different deferred methods. And when we chain thens, we basically are we're just building a chain of promises. So we can build out all of our code without the shape of nesting all of our callbacks, and just have them kind of define our callbacks that will define them sequentially without all the indentation and the nesting, and knowing that they will, each of the 3 callbacks can be invoked at any point if the promise down the line happens to be fulfilled or not, they can be invoked. So in an example of this is the DNS resolver. So usually the services in React are the things that actually return the promises. If you're dealing with the main server, the main stream libraries, the promises are at a much higher level than that. So in the DNS resolver, rather than having to deal with, OK, well, DNS resolve and then on resolution or have some other events, the DNS API basically just returns a deferred to us. And then, so resolve, in this case, I'm passing in, if I were to invoke this in the command line, I pass in the command argument. And then I'm basically skipping the progress update. I don't really care about that in this case. So just the success callback or the fulfillment callback and the error callback. And so on success, I'm just noting a callback that will be echo this out. And then I could chain multiple thens after this if I had multiple callbacks that depended thereafter. Just suggested reading on this is very easy to Google for, but it's called You're Missing the Point of Promises. This was helpful when I was starting off with React and trying to familiarize myself with, like, well, why would I use promises, or what is the reason for their implementation? This is a very helpful blog post to follow up on. So back to the React stack. So we mentioned having the streams at the lower level. So on top of this, we have a socket. And this is what's representing the TCP connection. So when we have a web server or we have like the Redis driver, we're actually creating sockets that are readable and writable connections. And so there's a server and a client context. So the server context, which we saw a little bit in the Hello World example, we could listen on a port and a host. We can access the port and basically shut down things. The main event for us is incoming connection. So an incoming connection comes in, and now we'll get a connection passed into our callback here. And so the different events on a connection, we'll notice that I'm kind of blurring out the stuff that it inherits. So a connection it implements the readable interface and a writable interface, so it's both of those streams. And it also, the only method that really adds is what is the remote address. Otherwise, it's just something we can read and write from. And so an example here, hopefully if you have a running Wi-Fi connection. So I have a chat server running. And if you just telnet to port 2012, connection refused. OK. I don't know if anyone else can get to this, but this is let me just go back to this. Is anyone able to telnet into that? Pretty sure I do have it running. Make sure my IP address is still the same. Yep. Try the actual IP. Oh, yes, sorry. This is from 2 years ago. Sorry about that. Great. Great. OK. So, well, you have fun with that. So what's basically going on here is we create that loop. We create a socket. And I'm going to use SPL object classes because those are great. I always try to find excuses to use SPL object storage or the exception classes, things like that. And so this is going to be the socket server. So just TCP connections. As connections come in, we basically want to track them so that we know who all the clients that are actively connected are. And each time there's data, basically we know we want to access what all the clients are, and we have the connection, and we know the data. So we know this is basically the person that sent the data, and these are all the other clients. So we're not going to echo the person's data back to them, but for everyone else, we're going to write out the data with their remote address attached to it. I used this earlier from my iPhone. There's no escaping here. So my iPhone, I was not able to quit Telnet from the terminal. And when I close the app, it just dumps a lot of garbage data. It doesn't stop. So maybe you're seeing that right now if somebody is posting bad Telnet commands in. When the connections actually end, we just want to detach it because we don't want to go try and write the data to people that are no longer connected. But it's pretty straightforward and totally contrived example. But basically, the bare minimum that it takes to have a multiple clients communicate with each other, and just using React as kind of a person to negotiate the data to and from. And let me jump back over here. OK. So the other case, and this is I'm just going to show a little about the process component. So at MongoDB, I work on the PHP driver, which is the C extension. And one of the things that we have in our test suite is we need to spin up like a whole cluster of machines and things like that. The Mongo command line shell has a bunch of nice utilities for this. And unfortunately, there's no API to access it from PHP. And I really wouldn't want to implement all the logic for spinning up like a shard cluster, replica sets, and things in PHP by itself. So what we wanted to do was basically connect to the Mongo shell and deal with its standard in, standard out, and kind of use the shell, trigger the shell commands from PHP. And how many people are familiar with server growth for PHP hosting? Somebody? OK. I guess this is one of the few conferences I've been to where they were not sponsoring the lanyards. So they have VPS hosting for PHP. And they were using React in a similar fashion to have like a web-based terminal with where you're using an AJAX terminal and it's sending data over to a terminal on the back end. But in my case, I need to deal with an actual forks process. So the child process component kind of has the same API as like popen. I basically just run a command. I have the process resource, and then I'm going to create my own standard out because I want to be able to write to my own stream back on the client side. I'll show an example of this in a second. The process has really not many events, but when the processes exit, I'll just basically close standard out. And this will also tell the event loop that there's no more streams. I'm not dealing with a process anymore, and my standard out is closed, so I could just return the PHP script, and the loop can end. But additionally, one of the caveats here, which we found out while implementing this, was we needed a way to kind of PHP doesn't have any convenient API for launching processes or setting up the standard in, standard out stuff. So we have to, kind of a lousy API decision, we have to kind of set a timer to basically run as soon as the loop starts, that's when I'm going to actually launch my process and start it. And the other thing, that gives us the opportunity to, we have to take the standard in, standard out, and standard error streams and just kind of wrap them in React streams and register them with the event loop. So all has to happen kind of as soon as possible. And then from there, we can, in this case, I just, as a proof of concept, is add timer to do something 1 second down the line. I'll just run a bunch of commands through the shell, and then exit. And this should all get echoed out back to the PHP shell. So just go. That's still going. Good luck with that. So this is basically the same script here. So this basically connects to the Mongo shell. I run true, that's me running the commands, right result. They come back with that, and then at the end I ask for them sorted in reverse order. And then once it actually exits, the event loop knows, well, there's no more, I'm not dealing with streams, my process is dead, so I'll just return to the user. And the data is actually in the actual Mongo shell. So. Happy that I could help in your self-promotion, Jeffrey. OK, so takeaways, lunch is coming right up. So when dealing with React, one of the things you definitely want to avoid is blocking at all possible. So you have callbacks at your disposal. And I'm sure the first time, I guess before the DNS component existed, Igor, did you find this out the hard way? That it was blocking when it was resolving domain names? Yeah. OK, right. So you'll run into cases where you're running, we get a PHP callback. I could call whatever PHP functions I want to do. I could do fwrites. I can launch another React loop within a PHP callback, whatever. But you have to be careful about what functions you might run that actually do happen to block. So whether that's DNS resolution, or doing something as innocuous as like file get contents on a small file. Those are all things that could end up blocking. And so the reason for all those services in React is to move as much of the I/O as possible into React's event loop, so that anytime the stuff that blocks is usually going to be I/O of some form. So anytime the I/O would block, then the event loop can go allow something else to interleave. So database queries are a huge thing. So using like any of the MySQL functions, even the MongoDB driver. Probably the AWS API could probably be easily ported over to React because it's a lot of network I/O. Doing things like disk and file I/O, so I mentioned like file get contents, file put contents, or just doing like your own fopen inside something innocuous, or maybe using like a logging library, which is also probably internally doing file I/O. So it kind of requires working with React, or in case of like Node.js, it's like an all-in approach where everything has to be kind of redesigned to work around the context of event loop and interleaving when there's things would otherwise block. Otherwise, the other thing is CPU-intensive tasks, which is really easy in PHP when you're working with arrays, or doing maybe like JSON encode on a very large, or JSON decode on a very large PHP object. And there's a blog post from Ted Zubia, I'm probably not pronouncing that right, but it was in 2012, and he was basically lambasting Node.js because he decided to use it for writing Fibonacci number calculations, which is a really stupid way to use Node.js, but it was obviously if you're writing some like heavy number crunching algorithm, you're not going to make use of the event loop at all. And so you're just going to block for the duration of that function. So some helpful tools that React has for this. So there's inter-process communication, like spawning a child process. I'll let that other process block if it needs to, but then your actual event loop can just wait when it has data to be emitted on standard in, standard out. Message queues, so using things like Redis or ZeroMQ, and just writing asynchronously to those, and then reading them the same way you might make like a background worker or a command process that maybe like watches your application and then decides to send emails offline, instead of using like Mandrill or Mailgun to just immediately send it from your application. And the other thing that React allows us is nexttick, which basically, if you want to say we are doing something like JSON decoding or some large algorithm that involves a lot of processing, we could break it into little pieces, maybe little callbacks that work on maybe 100 elements of the very large array, or 1,000 at a time, and just pass them incrementally to nexttick. So I'll basically, in my next loop tick, I'll process 100 array elements, and then I'll just say, on the next tick, I'll do the next 100. And so in between my processing, I'll allow other I/O to happen and other callbacks and requests to be served. There is something that I found buried in PHP in the MySQLi extension. So there's this MySQLi pull function, which is pretty neat. And so this could be used for asynchronously running MySQL queries. Unfortunately, this is completely different from like the stream polling that React does in its event loop. So this wouldn't totally be useful for, it would be more difficult to kind of port this over into React. But there is ways, if you're not even using React, if you're interested in doing like asynchronous MySQL queries and working with asynchronous results. So possibly a new idea that you can work on. So with Composer, it's very straightforward to install. There is a 0.4 is the current version. I think 0.4.1. But that has all the stuff that we covered today. And then just to cover some of the other interesting projects that were built with it. So Chris Bowden, which is Igor's other developer on the project, has a WebSockets library, which probably has a lot more visibility. A lot more people are familiar with Ratchet and WebSockets than they are probably with React, which it uses internally. So he has a number of presentations on this. The library is under C. Bowden on GitHub. And then if you're familiar with Alvaro Videra, he made GIF sockets, which is essentially WebSockets using animated GIF frames. And so this is great. This actually works in IE6. You can actually send data asynchronously, just basically in lieu of having like an AJAX request or an actual WebSocket, we could just keep the GIF open and keep sending the data over. I'm sorry if I'm supposed to be pronouncing it GIF. I'm in the GIF camp, so I'm sorry, or good job, but each other. At this point, we could break for lunch. I'm willing to take any questions from anyone other than Igor, because he would totally stump me on anything. And if you have any feedback, you could leave it any time in the next year. I'll get it whenever it's there. I'll just go look for it. But thanks for your time.